Hey everyone, it's Mr. Geiselman here to go through Newton's second law, or F equals ma, force equals mass times acceleration with you today. So Newton's second law by definition states a force exerted on an object is equal to the mass of that object times the acceleration of that object. So in this equation, force, mass, and acceleration are taken into account. And that really comes out to be the equation F equals m times a, or force equals mass times acceleration. So the force exerted on an object is equal to the mass of the object multiplied by its acceleration. And since Newton's second law talks about force, and force is new for us, the force unit is a Newton. So our new unit of force, all right, is a Newton. And in just a second, we're going to go over how you actually arrive at a Newton. So Newton's second law, again, it can be simplified as force is equal to mass times acceleration. When we look at force, we measure those in Newtons, obviously done by a capital N. That is our variable right there. Mass we measure in kilograms, and acceleration we measure in meters per second for standard units. Now, 1 Newton then is equal to 1 kilogram multiplied by 1 meters per second squared. So that's how we arrive at the force of a Newton. A Newton sometimes can also be called a kilogram times meters per second squared, but it's much, much easier to just call it Newton. So when we work with forces, we're working with Newtons. So the acceleration of the object is related to the size and the force and the mass. All right, so the larger the mass of an object, the more force it's going to need to accelerate that object. I think that's pretty intuitive. If you were trying to push something, the bigger that object is, the harder you need to push. Then again, the larger the force that is applied to that object, the greater the acceleration is going to be. And we're going to look at a PhET simulation to see this in action. So here I have a small crate, all right, that has a mass of 100 kilograms. And I'm going to apply some force to it with this little guy. So by doing that, I'm going to type in here, let's say 50 newtons worth of force. When I click off of this, my little guy here is going to apply a force of 50 newtons to that crate to the right. So let's see how that affects it. You can see that that crate continues to move at a constant acceleration to the right as that force is continually applied. So if force equals mass times acceleration, we said that a larger force would then give us a larger acceleration if the mass stayed the same. So the mass has not changed. Our small crate still has a mass of 100 kilograms. And now we're going to apply a force of 100 newtons instead of 50. And we're going to see what happens. Now that force is a little bit bigger, and that object accelerates faster. Let's take a look if I change this force to 10 newtons. Now my force has decreased, the mass has stayed the same. What should happen to my acceleration? My acceleration should go down. So now that acceleration, that object is barely accelerating as only 10 newtons worth of force is applied to it. If I wanted to change this up, I want to make the object bigger. I have now changed my mass to the mass of this refrigerator that has a mass of 200 kilograms. So my object is much bigger, so I'm going to need a larger force to move it at the same rate as it was before. So if I set this to 50 newtons, if I set the force to 50 newtons, you can see that that force is very, very small, right? And it's not going to really move the refrigerator much. If I change this number to 100, newtons. Oops, 100 newtons. Now that force is a little bit bigger, not enough though to get it moving. So we're going to crank it up to 128, or how about 150? 150. Now my refrigerator is moving. All right. So I have to apply a large enough force to get the object moving, and now it will accelerate. So let's say we put this force up to 500. Now it's accelerating at a much faster rate, and it's changing its velocity much faster, right? What would happen if we changed that we kept the Newton force, or just the force, at that same 500, and we changed it to a dog, right? I have now reduced the mass to 25 kilograms. You can see it is a much smaller object. So by applying the same force, that same 500 newtons, my acceleration is going to be much greater. And the dog moves much quicker. So force equals mass times acceleration, right? To change an object's motion, an unbalanced force must act upon it. So an object in motion will stay in motion until it's acted upon by an outside force, right? And an object at rest will stay at rest until it's acted upon by an outside force. In the video we're going to watch, there are two forces, both going in opposite directions. Force number one has a mass of 90 kilograms and 1.85 meters per second squared for an acceleration. Object number two has a mass of 110 kilograms and an acceleration of 1.8 meters per second squared. Which one is a larger force, and then going to impose that force on it? So these two are opposing forces. Which one is going to be greater, and which one then is going to overcome the other? Well, if you did the math, you figured out that the first one, 90 kilograms times 1.85 meters per second squared, is equal to 166 newtons, where the 110 kilogram object with the 1.8 meters per second squared acceleration has a much larger 198 newton force. Let's see if that's true here in the video. So does force equals mass times acceleration? So which player had the larger force? The player in the red jersey did. He had a much larger force and then was able to change the other player's direction. We can figure that out using Newton's second law. So using Newton's second law, we can do a little bit of math and we can figure out a few new things. So with Newton's second law, we know that force is equal to mass times acceleration. So the scenario has a force, asks us what force from the car's engine, what is the force from the car's engine if it has a mass of 3,000 kilograms and accelerates at 2 meters per second, right? Obviously, it tells us exactly what we're looking for right away. What is the force? So we are going to put a question mark there in our problem because we don't know that. It tells us our mass of 3,000 kilograms, and it tells us our acceleration of 2 meters per second squared. If I was going to draw this as a force diagram, the force applied by the engine is in one direction. There is no balancing force in this equation. It tells us there is no force acting opposite of it. So it is an unbalanced equation. And now we have force equals mass times acceleration. We can find our new mass. If we substitute our numbers in, we still are looking for force, and we know that 3,000 kilograms and we know that the acceleration is 2 meters per second squared. When we multiply a kilogram by meters per second squared, we get a Newton, and 3,000 times 2,000 gives us our answer of 6,000 newtons. Our next problem says that a 10 kilogram box is pushed with a force of 100 newtons. Friction works against the box, or against it, with a force of 20 newtons. What is the acceleration of the box? So first off, I know its mass is equal to 10 kilograms. It says it right there in the problem. But now we have a applied force of 100 newtons and friction working against it with 20 newtons. To find our net force that is going to impact this problem, we need to use our force diagram. I know that we are applying our force applied is equal to 100 newtons, and I know that my force of friction is equal to 20 newtons. 100 newtons to the right minus 20 newtons to the left is going to equal 80 newtons in this direction. So my net force is going to be 80 newtons. Because this force diagram is unbalanced, we choose unbalanced for that option. And now we can write in our equation of F equals ma. Force is equal to mass times acceleration. And we now can substitute and solve. We know that 80 newtons is equal to our mass of 10 kilograms times our acceleration, which we still don't know. To get A all by itself, I'm going to divide both sides by 10 kilograms. And when I take a Newton divided by a kilogram, I'm left with a meter per second squared. And when I solve this problem, 80 divided by 10 is going to be 8 meters per second squared for our answer. Our final problem has a hockey player being pushed on his skates, or pushing forward from his skates, with a force of 147 newtons against a frictional force of 2 newtons. His acceleration is 3 meters per second. What is his mass? Because it's telling us right in the question we want to find his mass, I'm going to put a big question mark there in mass. I'm told right away that his acceleration is 3 meters per second squared. And now to find his net force, I need to make my force diagram. My force applied, right? So the force the hockey player pushes is going to equal 147 newtons. The force of friction in the other direction is equal to 2 newtons. 147 minus 2 gives us an answer of 145 newtons, and that's our new net force. Because it's not zero, it is an unbalanced equation, and I can now write my F equals ma equation. I can sub in 145 newtons, set that equal to our mass, which we still don't know, times our acceleration of 3 meters per second squared. If I divide both sides by 3 meters per second squared, I can solve for our answer. we know that a Newton divided by a meter per second squared is equal to kilograms. And when we take 145 divided by 3, we get an answer of 48.3 repeating kilograms. So that is our mass for our hockey player. I hope this helped. I hope you guys understand it. If you don't, please let me know. Reach out to Mr. Oleg, Mr. Swenson, or myself. Have a great day, everyone.